Hello students, I hope you all are fine and healthy. We are reading chapter number 3, Atoms and Molecules. In our previous videos, we have already learned what is an atom. So do you remember what is an atom? An atom is the smallest particle of an element which can take part in a chemical reaction. All the kinds of elements are made up of atoms. Generally, the atoms of most of the elements, they are very reactive and they do not exist in free state. It means that they do not exist in the form of single atom. They either combines with the atoms of same element or with the atoms of different elements. Because they are very reactive, so either they react with the atoms of the same element or they react with the atoms of different elements. And the atoms of different types of element are different. So the types of the atoms that are found, they are equal to the types of the element. We already know that the atoms are very small in size. So if we will arrange 3 crore 50 lakhs copper atoms in a single straight line, then they will cover a distance of approximately 1 centimeter. Isn't it a very small distance? Yes, it is a very small distance. So if these large number of atoms covers only 1 centimeter, then we can easily assume that the size of the atoms will be very small. Or we can say it will be extremely small. Now the size of an atom is measured by its radius, which is known as atomic radius. Atomic radius means the radius of an atom. So the size of an atom is measured in the units of nanometers. Nanometers is a very small unit of measuring length. Now 1 nanometer is equal to 1 upon 10 to the power 9 meter, or we can write it as 10 to the power minus 9 meter. So that is a very small unit. The smallest atom that is found is of hydrogen. The atomic radius, or we can say the size of the hydrogen atom, is equal to 0.37 nanometer. If we will express it in meter, then we will get 0.0000000037 meter. So it is a very small number. That's why the hydrogen atom will be very smaller in size. The atoms are so small in size that we cannot see them even with the most powerful optical microscope. Optical microscope are those microscopes which use light for their working. We can only see the enlarged pictures of the atoms that are present on the surface of an element by using an electron microscope. Now the electron microscope uses electron for its working. We already read that the electrons are present inside an atom. Instead of using the full name of an element while writing a chemical equation, we use its symbol. Since the elements are made up of atoms, so the symbol of elements means the symbol of atoms of elements. So the symbol of the element represents the atoms of that element. Symbols are a short way of representing an element. Just like we use many abbreviations in our everyday life, similarly we use symbols for writing a chemical equation. Now John Dalton, he was the first scientist to use the symbols of an element. His symbols represented the elements as well as one atom of that element. So some of the symbols that were used by the Dalton are: for hydrogen, he used a circle that is having a dot inside. For carbon, he used a colored circle. Whereas for oxygen, he used an empty circle. And for phosphorus, the symbol is just like the logo of the Mercedes. Whereas for the sulfur, inside the circle, a plus sign is drawn. For platinum, the letter P is written inside a circle. And for iron, the letter I is written inside a circle. For copper, the letter C is written inside a circle. And for silver, the letter S is written inside a circle. Whereas for gold, the letter G is written inside a circle, and there are many small lines that points towards the inside. Whereas for the lead, the letter L is written inside the circle. And for mercury, there are 8 small dots that are arranged inside a circle. So these are some of the symbols that are used by the Dalton. As we can see that it is difficult to draw the Dalton symbol. That's why they are not used nowadays. They are only of historical importance. J.J. Berzelius, who was another scientist from Sweden, he said that either the first letter or first letter with another letter from the name of an element should be used as its symbol. Either we use the first letter, or in some cases we have to use one more letter with the first letter from the name of the element. So the modern day symbols are based on the idea that was given by the J.J. Berzelius. The symbol of an element is either the first letter or first letter with another letter, either of its English name or Latin name of an element. For example, the H symbol is used for hydrogen, and P is used for phosphorus, and B is used for boron. So in these 3 cases, the first letter of the name of element is used as its symbol. Now the name of some elements begin with the same letter, like in case of boron, barium and bromine. So in these types of cases, one of the element is given a single letter symbol and other elements are given 2 letter symbol. Like the letter B is used as a symbol of boron, and Br is used for bromine, and Ba it is used for barium. Similarly, in the case of carbon, calcium, chlorine and copper, their name starts with the letter C. So in these case, the carbon, it is given a single letter symbol, that is C, whereas Ca, it is used as the symbol for calcium, and Cl is used for chlorine, whereas Cu is used for copper. As we can see in these cases, here the first letter is given the symbol of the name of element, and in this case the first and the second letter is used as the symbol, whereas in case of chlorine the first letter and the third letter is used as the symbol. Whereas in the case of copper, the symbol has been derived from its Latin name. So the another letter in the symbol may or may not be the second letter of the name of the element. It can be any letter. And whenever we write the symbol of an element, the first letter is always capital, whereas the second letter is always written in small letters. Some of the symbols of the elements are derived from the Latin names of the elements. Since we use the English names of the elements in our everyday life, so sometimes we get confused about their symbols. So these are the symbols that have been derived from the Latin names of some elements. Like for sodium, we use the symbol Na, that is derived from its Latin name natrium. For potassium, the symbol K is used, which is derived from the Latin name kalium. And for iron, we use the symbol Fe, which is derived from the word ferrum. For copper, the symbol Cu is used, which is derived from the word cuprum. Similarly, for silver, we use the symbol Ag, that is derived from the Latin word argentum. And for gold, the symbol Au is used, which is derived from the word aurum. For mercury, the symbol Hg is used, that is derived from the word hydragyrum. And for lead, Pb is used, which is derived from the word plumbum. And for tin, the symbol Sn is used, which is derived from the Latin name stannum. So you have to learn these symbols properly because you might get confused in them. The symbol of an element not only represents that element, but along with that it represents many other things. Like the symbol of an element represents the name of an element, it also represents one atom of that element. It also represents 1 mole of atoms of that element. 1 mole means 6.022 into 10 to the power 23 atoms of that element. So if we say that 1 mole, it means 6.022 into 10 to the power 23 atoms. It also represents a definite mass of an element. It means it represents the atomic mass of the element in grams.
Now we will discuss some questions related to this chapter. So our first question is, name the international organization who approves names of elements. Now the second part of the question is, give an example to show that the law of conservation of mass applies to physical changes also. So the international organization who approves the names of elements is IUPAC. Now the full form of IUPAC is International Union of Pure and Applied Chemistry. Now the second answer is, we can take the example of melting of ice into water, because melting of ice into water is a physical change. So what we will do, we will take a piece of ice in a conical flask, and what we will do, we will put a rubber cork on it. Now we will measure the weight of the conical flask along with the piece of ice. Now this will be, suppose, W grams, that is with the ice. Now what we will do, we will heat the flask slowly. Now what will happen when we will heat it? The ice will start converting into liquid water. So after some time, all the ice will melt and form liquid water. Now we are going to again measure the weight of the conical flask. Now suppose this is again W grams. This is the weight of liquid water. Okay. Now what we will find that there will be no change in the weight. Means the weight of ice will be equal to the weight of water. So it shows that the law of conservation of mass applies to the physical changes also. Now our second question is, when 3.0 gram of carbon is burnt in 8.0 grams of oxygen, so 11.0 grams of carbon dioxide is produced. Now what mass of carbon dioxide will be formed when 3.0 grams of carbon is burnt in 5.0 grams of oxygen? Now which law of chemical combination will govern your answer? State the law. Now when 3.0 grams of carbon is burnt in 8.0 grams of oxygen, so 11.0 grams of carbon dioxide is produced. Now it means that the carbon and oxygen, they are combined in the ratio of 3:8 to form carbon dioxide. So when 3 grams of carbon and 50 grams of oxygen will be there, then also 8 gram of oxygen will be used and 11 gram of carbon dioxide will be formed. Now the remaining oxygen will remain unused. Okay. Now this reaction is governed by the law of constant proportion, or we can say the law of definite proportion. According to the law of constant proportion, a, a compound is always made up of same elements that are combined in the same ratio by their mass. Okay, so all the pure compounds, they contain same elements which are combined together in the same proportion by their mass. Now the next question is, with the help of a label diagram, describe an activity to demonstrate the law of conservation of mass. So here the diagram is given. Now what we have to do, we have to take a conical flask. Now what we will do, we will take sodium hydroxide and copper sulfate. Now we are going to prepare the solution of sodium hydroxide and copper sulfate by dissolving them in small amount of water. Now what we have to do, we will take the copper sulfate solution in the conical flask and sodium hydroxide solution is in a small test tube. Now we will tie a thread at the mouth of the small test tube, and then we will hang this test tube inside the conical flask. Now we will hold the thread, fix the thread with the help of a rubber cork. Now we will place the test tube in such a way so that the sodium hydroxide solution do not get mixed with the copper sulfate solution initially. Now what we will do, we will measure the mass of the apparatus with the solutions. Now what we will do, we will again mix the solutions. Now what we will find, we will again, when we will again measure the mass of the solutions, or we can say mass of the apparatus after mixing both the solutions. So the mass of the apparatus with the products, it will be the same as it was with the reactants. Like in this diagram, it was shown that the mass of the apparatus along with the reactants is 67.25 gram, and the mass of the apparatus with the products, it is also 67.25 gram. So this shows that the mass of the reactants is equals to the mass of the products. Okay. So with the help of this activity, we can demonstrate the law of conservation of mass. Now the next question is, define Avogadro number and convert 2 moles of magnesium sulfate sample into number of molecules present in the samples. Now we know that Avogadro number means the number of particles that can be atoms, molecules or ions which are present in 1 mole of any substance is fixed. Now its value is 6.022 into 10 to the power 23. Now this value has been found experimentally. So this number is known as the Avogadro constant, or we can say it is also known as Avogadro number, okay, which is represented by N naught. Now to find the number of molecules in 2 moles of magnesium, we will multiply 2 with the Avogadro number, that is 6.022 into 10 to the power 23. So it will give us 12.044 into 10 to the power 23. So these number of molecules will be there in 2 moles of magnesium sulfate. Now our next question is, 10 grams of calcium carbonate produces 3.8 grams of carbon dioxide and 6.2 grams of calcium oxide. Now we have to represent this reaction in terms of law of conservation of mass. Now according to the law of conservation of mass, the total mass of the reactants is equal to the total mass of the products. So here we will see that the reactant is calcium carbonate and the products formed are carbon dioxide and calcium oxide. So the mass of reactant is 10 grams and the mass of products is 3.8 grams of carbon dioxide and 6.2 grams of calcium oxide. So 10 grams of calcium carbonate will be equals to 3.8 grams of carbon dioxide plus 6.2 grams of calcium oxide. Now 3.8 plus 6.2, that gives us 10 grams. So 10 grams of reactant is equals to the 10 grams of products. So in this way we can represent this reaction in the terms of law of conservation of mass. Now our next question is, in a reaction 5.3 grams of sodium carbonate reacted with 6 grams of ethanoic acid. Now the products were 2.2 grams of carbon dioxide, 0.9 grams of water and 8.2 grams of sodium ethanoate. Now show that these observations are in agreement with the law of conservation of mass. Now according to the law of conservation of mass, the total mass of the reactants is always equals to the total mass of the products. So it means here the reactants are sodium carbonate and ethanoic acid. So they both reacts and gives carbon dioxide, water and sodium ethanoate. Okay. So I have written it in the form of a reaction also. Now the mass of sodium carbonate and ethanoic acid, it should be equal to the mass of carbon dioxide, water and sodium ethanoate. So mass of sodium carbonate is 5.3 grams and the mass of ethanoic acid is 6 grams. So 5.3 grams plus 6 grams. It should be equal to the mass of carbon dioxide, that is 2.2 grams, plus mass of water, that is 0.9 grams, and mass of sodium ethanoate, that is 8.2 grams. So now 5.3 grams plus 6 grams, that is equals to 11.3 grams. Now 2.2 plus 0.9 plus 8.2, that is also equals to 11.3 grams. So we can see here the mass of the reactants is equal to the mass of the products. So these observations are in agreement with the law of conservation of mass. Now our next question is, what is the significance of the symbol of an element? Explain with the help of an example. Now the symbol of an element, it represents many things. Like the symbol of an element represents the name of the element. It also represents one atom of the element. Now, the symbol also represents 1 mole of atoms of that element. It means that the symbol also represents 6.022 into 10 to the power 23 atoms of that element. Now the symbol also represents a definite mass of the element, that is equal to the atomic mass expressed in the grams. So these are the questions